Half-Life, which is a great game if you get a chance to play in it, Half-Life 2 particularly. Right, so let's have a look at this then. Half-Life is a term used to describe a predictable effect of atoms that decay. Now, the problem with radioactive decay, it is actually a random event, much like the lottery is a random event. But there are some things you can predict, and one of them is the half-life. You need to know the following things. You may be asked this. They may say, define what we mean by half-life. And you can remember this word for word. Half-life of a radioactive isotope is the average time it takes for the number of nuclei in the isotope, of the isotope in a sample to half. You need to remember that word for word. Well worth doing a card on that. Activity, basically this is the number of nuclei that decay each second. Okay, so 3,000 becquerels, which is the unit of activity, would mean 3,000 decays every second. 3,000 nuclei have decayed. And activity and the number of nuclei both decrease by half in a half-life. So if you had, say, a count rate of, say, 3,000 becquerels, as it's called, you don't need to know the unit of that, by the way, then if an hour later they'd gone from 3,000, say, to 1,500, you would say the half-life is 1 hour. Why are some isotopes radioactive? Well, it's because they have too many neutrons. Sometimes it can be because they have too few neutrons, but it is all to do with the neutrons. They have a set of amount of neutrons that the atom or nucleus is not particularly happy with. What is an isotope? Well, an isotope of an element has different numbers of neutrons but the same number of protons. This is covered in another video, but again, it's something that you need to memorize, that it has different numbers of neutrons but same numbers of protons. We're going to look at a practical example here of half-life here, and a good demonstration of this is considering the age of a piece of organic material. Okay, now we can work out how old a piece of organic material is by looking at the amount of carbon-14 it's got in it. There have been cases in the past where bog bodies, these are bodies that are buried in Denmark that are thousands of years old, are discovered, and the police have to wonder, well, hold on, is this a recent death, or is it something longer than that? And you can use carbon-14 dating for working out how old something is. I'm going to demonstrate it now. So we've got a fish there with 8 carbon atoms. Obviously it'd be 8 trillion carbon atoms, and these are carbon-14 atoms. Normal carbon atoms are carbon-12, but these are carbon-14, which means it's got extra neutrons, and that makes it unstable. And over a period of time, those carbon-14 atoms will change to nitrogen-14, and you can see that in the next diagram. It's gone from 8 carbons to 4 carbons and 4 nitrogens. Another half-life later, well, it does this. It goes down to 2 carbons and 6 nitrogens, and another half-life later it goes to 1 carbon. Now, a lot of students think that when you have 2 half-lives, it would have all gone. No, it wouldn't have. You can see it's gone from 8 carbons to 4 carbons to 2 carbons to 1 carbon. What you have here is 3 half-lives. Okay, it's 3 half-lives is what you've got there. And as it happens, the half-life of carbon, I believe, is something like 6,000 years, 5,400 years. So for it to reach this sort of process would have taken 3 lots of 5,600 years, which is something like 16,800 years it would have taken to reach that stage. And that can be plotted in a graph like you see here. It shows you the number of carbon-14 atoms on the left-hand side, and along the bottom are the time in years. So you start off with 8 atoms. Of course, you're talking about 8 trillion atoms. Then 6,000 years after that, you'd have 4 atoms left. Then after 12,000 years, there'd be 2 atoms, and after 18,000, there'd be 1 atom. So you can see that decay, and that's the classic shape of half-lives. It has that shape. And by comparing the number of nitrogens with carbon, you can work out how old the rock actually was. The uses of this technique is it allows us to work at the ages of rocks. It allows us to work at the age of the Earth. We know the Earth is 4.6 billion years old, or 4,600 million years old. You don't need to know that for the exam. And it also allows us to work out the age of organic material. Right, the key words you need to make sure you understand. Make sure you know what we mean by isotopes, by half-life, activity. Know that it's a random event. We cannot predict any individual nucleus decaying, but when you get a sample of 1 million or whatever, then you know that roughly half of them are going to disappear after a half-life. In the same way that in a lottery, we don't know which numbers are going to come out, but we know that at least 6 numbers are going to be taken out every week in the national lottery. And then finally you've got the count rate as well. The count rate is the number of decays per second that are detected. And there you go. That is what I mean by half-lives.